Welcome to Lecture 7A, Quantum Computing. I've given a title to this lecture as Quantum Fourier Transform, from classical signals to quantum superposition. This is your professor Atif Reed Muhammad, Marshall University, West Virginia. So welcome to this module on Quantum Fourier Transform, or QFT for short. This module sits right at the heart of quantum computing. It is the algorithm that makes many other powerful quantum algorithms possible. If you understand the QFT, you will have the solid foundation for understanding why quantum computers can outperform classical computers on certain tasks. Before we dive in, think about what you already know about waves and signals. When you listen to music, your speakers turn electrical signals into sound. Behind the scenes, engineers use a mathematical tool called the Fourier transform to break those signals apart and put them back together. The QFT is the quantum version of that same idea, but it works within quantum bits or qubits instead of ordinary numbers. By the end of this module, you will know what QFT is, how it is built from basic quantum gates, why it is so much faster than its classical cousin, and how algorithms like Shor's famous factoring algorithm use it to solve problems that would take a classical computer longer than the age of the universe to crack. This slide gives you a map of the journey we are about to talk. We'll start by the big picture, what the Fourier transform actually does in plain terms, and then compare the classical version called the DFT with the quantum version, the QFT. Understanding both side by side will make the differences much clearer. From there, we will dig into the math behind the QFT. Don't have to panic. We'll build up slowly, starting with the core idea and then breaking each piece into something understandable. We will also look at the quantum circuit that implements the QFT, identifying which gates are used and why each one is necessary. In the final selection, we will connect all of this to real applications, phase estimation, Shor's algorithm, and quantum chemistry simulations to rely on the QFT. We will also be honest about the challenges. Real quantum hardware is difficult to build, and noise remains a major obstacle. Let's get started. Imagine you are standing outside a building and you hear music playing inside. You can hear the whole chord, the sum of all the notes mixed together, but you want to know which individual notes are being played. The Fourier transform is the mathematical tool that does exactly that. It takes a complicated signal and breaks it down into pure simple frequency components. This idea is used everywhere in modern life. When you stream a song, the audio file has been compressed using Fourier analysis to remove frequencies your ears cannot hear anyway. MRI machines in hospitals use Fourier transform to convert raw scan data into the images doctors look at. The Wi-Fi routers use it to send and receive data reliably by separating signals from the noise. The key insight is that any signal, no matter how complicated, can be thought of as a sum of simple waves. The Fourier transform finds the recipe, how much of each frequency is in the mix. The quantum Fourier transform does the same thing, but the signal is a quantum state and the recipe is encoded in the phases of qubits rather than in a list of classical numbers. So you can look at the DFT formula and the breakdown I have given. This will allow you to look at the complex number that rotates on the unit circle. It encodes frequency k, and the complex numbers we have discussed in one of our previous discussions as well. So the classical discrete Fourier transform, or DFT, works on the list of numbers. Think of the list as a digital signal, like the recorded volume of the sound sampled thousands of times per second. The DFT produces a new list of the same length, where each number tells us how strongly a particular frequency appears in the original signal. The way it works is straightforward. In concept, for each output frequency you want to find, you go through every signal in terms of every single input sample, multiply it by special rotating value that vibrates at the frequency, and then add everything up. You repeat this process for every frequency from the lowest to the highest. Each output value answers the question, how much does the particular frequency is hiding in the original signal. The rotating value used in the DFT, as discussed in the previous slide, are complex numbers. Numbers that have both a size and a direction, like an arrow that can point anywhere on a circle. As the frequency number increases, the arrow spins faster and faster around the circle. Slow spinning corresponds to low frequency, fast spinning corresponds to high frequency. This idea of spinning arrows on a circle is exactly what quantum Fourier transform inherits and works with. So there is a fundamental problem with the DFT. It is slow for large inputs. To compute a single output value, you need to do as many multiplications as there are input samples. To compute all output values, you need to repeat that work for every frequency, meaning the total number of operations grow as the square of the input size. For small signals, this is fine, but modern applications deal with millions or billions of data points, and squaring that number becomes unworkable very quickly. Engineers developed the fast Fourier transform in the 1960s to help the FFT, fast Fourier transform. Cleverly rearranges the calculation and dramatically reduces the number of operations needed. For a million data points, the FFT might need 20 million operations instead of 1 trillion, a massive improvement, but still limited when the input size gets astronomically large. Here is where the quantum Fourier transform, or QFT, changes everything. For a small number of qubits, say 30, those qubits can represent over a billion values simultaneously in superposition. The QFT transforms all of those values using only around 900 gate operations. Compare that to 30 billion for the FFT or a quintillion for the DFT, and you begin to see why the QFT is so extraordinary. This exponential gap is what makes it one of the most important algorithms in all of quantum computing. The quantum Fourier transform is the quantum computing equivalent of DFT. It takes a quantum state, a superposition of many basis states, and transforms it into a different superposition that represents the frequency content of the original state. The mathematical relationship is nearly identical to the classical DFT, but everything is written in the language of qubits and quantum mechanics. The big difference is power, because qubits can exist in superposition, being many values simultaneously. The QFT can process an astronomically large number of input values in parallel using only a small number of qubits. Classically, you need a separate number for each input value. Quantum mechanically, A handful of qubits encode all of them at once, and the QFT transforms this entire superposition in a number of steps that grows only as the square of the number of qubits. However, there is an important catch we'll return to later. You cannot simply run the QFT and then read out all the frequency values because measuring quantum state collapses it just to one outcome, as we discussed earlier. The real power of QFT comes when using its outputs at a step inside a larger algorithm that is specifically designed to extract the answer we need without throwing away the quantum advantage. To understand the QFT, we need to be clear on what a qubit is. A classical bit is like a light switch. It is either on or off, 0 or 1, as we discussed in length earlier. A qubit is more like a spinning coin. While it is in the air, it is neither heads nor tails, as we practically have looked at that. But some combinations of both at the same time, this is called superposition. While in superposition, the qubits has an amplitude for being 0 and an amplitude for being 1. And these amplitudes are complex numbers that carry both size and direction. The critical point for the QFT is what happens when you have multiple qubits together. With one qubit, you can represent two states simultaneously. With two qubits, you can represent four. With 10 qubits, you can represent over 1,000 states all at once. With 50 qubits, the number of simultaneous states exceeds a quadrillion, far more than any classical supercomputer can hold in memory. This exponential growth is representational power of the foundation of quantum computing advantage. Phase is the other key concept here. Not only does a qubit have a probability of being 0 or 1, it also has a phase, a kind of direction encoded as a point on a circle. The QFT does its work by manipulating these phases very carefully. After the QFT runs, the frequency information of the original state is stored in the relative phases of the output qubits. Reading that phase information cleverly is what makes the whole algorithm useful in practice. So the key points for QFT is n qubits can represent 2 raised to the power n values simultaneously. So while 10 qubits can work with 1024 states at once, 50 as I just mentioned. So the exponential power is what makes QFT, quantum computing, so remarkable. The formal definition of the QFT says that it takes a basis state representing some input numbers and convert it into an equal superposition of all possible output states, where each output state is weighted by a phase factor. The phase factor for each output depends on both the input number and the output label, and it corresponds to the specific point on the unit circle in the complex plane. Let us unpack that in plain terms. Imagine the input is just the number 7 stored as a quantum state. The QFT does not give you one output state for 7. Instead, it gives you a superposition of every possible output label from 0 up to the maximum, but each one has different phase, a different angle on the circle. Low output label get gentle phase rotation. A high output label get rapid phase rotations. The result is a quantum state that has encoded in its phases all the frequency information about the original input. The normalizing factor out front, 1 divided by the square root of the total number of states. It's just bookkeeping. It ensures that the total probability of finding the qubits in any state still adds up to 100%, as as quantum mechanics requires. Without it, the mathematics would not be physically consistent. With it, the QFT is proper quantum operation, meaning it is reversible and preserves the total probability of the system. Complex numbers are the backbone of the QFT, so it is worth making sure they make sense. A complex number has a real part and an imaginary part. You can also think of it as point in two-dimensional plane, described by the size and the angle. The size tells us how far from the origin the point is, and the angle tells us which direction it is pointing. When the size is exactly 1, the complex number sits on what is called the unit circle, as the angle goes from 0 all the way around the full circle. The point travels around that circle exactly once. Different frequencies in the QFT corresponds to different speeds of travel around the circle. A low frequency means the point barely moves. A high frequency means the point spins rapidly. The QFT uses these different notation speeds to separate out which frequencies are present in the input, just like the prism separates white light into colors based on their different wavelengths. Phase refers to where on the circle a particular point sits, the angle. When we say the QFT stores frequency information in phase, we mean it arranges the output qubits so that their angles encode which frequencies are in or were in the input. This is also why measuring a qubit destroys the information. When you measure, you force the qubit to commit to just one value and all the phase information is lost. The QFT is not useful because of what you can measure directly. It is useful because of what the phase structure allows subsequent quantum operations to do. So the key insight here is the QFT encodes frequency information in the phase angle of the qubit states, not in probabilities. So hopefully this makes sense. All right. Looking at the DFT and QFT side by side really brings home how similar they are in purpose but how different they are in power. Both transforms take some form of input and produce a frequency domain output. Both are based on the same underlying idea of multiplying by rotating complex numbers and summing the results. The quantum version is not some completely alien concept. It is a direct translation of a classical algorithm into quantum world. The critical differences are in the input and the output and the speed. The DFT works on a list of classical numbers and produces a list of classical frequency values that we can freely read as many times as we like. The QFT works on a quantum superposition of basis states and produce another superposition. We cannot directly read all the output values. Measuring collapses the state to just one. This limitation of means the QFT must always be part of the larger algorithm. The speed difference is where the quantum advantage truly shows. The classical DFT scales as the square of the input size. The FFT is much better, scaling as the input size multiplied by the logarithm of the input size. But the QFT scales only as the square of the number of qubits, which is the logarithm of the number of values being processed. For large inputs, this difference is not just constant factor improvement, it is an exponential leap. The difference between waiting a lifetime and getting an answer in seconds. The entire QFT circuit is built from just two types of quantum gates. This is one of the most elegant things that about it. A transform that achieves exponential speed up requires surprisingly simple components. The first is Hadamard gate. When we feed it a qubit in state 0, it puts the qubit into an equal superposition of 0 and 1. When we feed it to qubit in state 1, we get the same equal mixture but with a minus 1 sign or minus sign on the 1 component. The phase is flipped. The phase difference is what the QFT uses to encode frequency information. The second type of controlled phase rotation gate. This gate does nothing if the control qubit is in the state 0, but if the control qubit is in state 1, it rotates the phase to the target qubit by a specific angle for a larger value of the gate's index. The rotation angle becomes smaller and finer. When the index is 1, the rotation is a half turn. When the index is 2, it is quarter turn. When the index is 3, it is eighth of a turn, and so on, getting progressively finer with each step. Together, these two gates do all the work. The Hadamard gate creates a superposition, the both frequencies at once structure. The phase rotation gates tune the phases precisely so that after all the gates have run, the output qubit phases encode the frequency content of the input state. It is analogous to how a prism splits white light into a spectrum of colors, except here the colors are frequencies of quantum information being separated out by careful manipulation of quantum phase. For a 3 qubit QFT, the circuit follows a clear and beautiful pattern. The first qubit receives a Hadamard gate, then a controlled phase rotation with index 2 controlled by the second qubit, then a controlled phase rotation with index 3 controlled by the third qubit. These three operations together encode all the frequency information that the first qubit needs in its phase. The second qubit then receives a Hadamard and a controlled phase rotation with index 2 controlled by the third qubit. The third qubit receives just a single Hadamard gate. Notice the pattern. The number of gates applied to each qubit decreases as you move down through the qubits. The first qubit gets the most gates, the last qubit gets the fewest. This is because the first qubit needs the finest frequency resolution and so requires the most phase adjustments, while the last qubit only needs a coarse split and a single Hadamard is enough. For a general circuit with many qubits, the total number of gates grows as a triangle, the sum from 1 up to the number of qubits, which is proportional to the square of the number of qubits. This is where the quadratic scaling of the QFT comes from. After all the Hadamard and phase rotation gates have been applied, the qubits are in the correct quantum state, but the reverse order compared to the standard output convention. So the final step is a series of swap gates that reserves in terms of reversing the qubit order. For a circuit that many qubits, you need roughly half as many swap gates as qubits, and that is the complete QFT circuit. Elegant, structured, and impressively compact for the enormous computational power it delivers. Let us count the gates carefully. For a circuit with a given number of qubits, the QFT uses exactly one Hadamard gate per qubit, then a decreasing number of controlled phase rotation gates for each qubit, and finally a set of swap gates at the end of to reorder the output. Adding all these up gives a total number that grows roughly as the square of the number of qubits. In computer science notation, we call this quadratic scaling. Double the number of qubits and the gate count roughly quadruples. Now compare this to what those qubits actually represent. A small number of qubits can hold an astronomically large numbers of values in superposition simultaneously because the number of simultaneous states is 2 raised to the power of the number of qubits. The classical DFT on that same number of values would need a number of operations equal to the square of the number of values, which is 2 raised to twice the power of the qubit count. So the number is 2. The QFT only needs the square of the qubit count itself. That is an exponential difference, not just a constant factor improvement. To put real intuition on this, imagine 30 qubits. Those 30 qubits can represent over a billion values in superposition at once. The classical DFT on a billion values would need around 1 million trillion operations. The classical FFT would need around 30 billion operations. The QFT needs around 900 gate options. That is the quantum advantage in concrete terms, not a small speed up, but an exponential chasm between what classical and quantum computers can do on this specific task. At this point, you might be wondering, if the QFT is so fast, why do we want to use it for everything? Why not just run it and road off all the frequencies? The answer lies in one of the most fundamental rules of quantum mechanics. Measurement collapses a quantum state when you measure a qubit. It randomly picks one outcome based on its probability amplitude and loses all superposition forever. You get the sample from the distribution, not the entire distribution at once. So after running the QFT, you have a beautiful superposition of all frequency components. But the moment you try to look at it, most of that information disappears. You cannot get it all out. This is not a limitation of our technology that we might fix it in the future. It is hard law physics. No matter how perfect our quantum computers become, we will never be able to read an exponentially large amount of information from a single measurement, because doing so would violate the fundamental postulates of quantum mechanics. This means that QFT is never used as a standalone algorithm. It is always a subroutine, a carefully designed step inside a larger quantum algorithm. The surrounding algorithms must be engineered so that the specific piece of information that we need gets amplified into something we can reliably measure, while the irrelevant information is suppressed. Phase estimation and Shor's algorithm are the two most famous examples of doing exactly this. They are brilliant because they extract just the right answer from QFT output without needing to see everything at once. Quantum phase estimation, often abbreviated as QPE, is the most direct and important application in of the QFT. Here's the problem it solves. In quantum computing, the quantum chemistry, we often work with special quantum operations called unitaries. A unitary or unitaries, let me correct myself, my pronunciation. So let me repeat. We often work with special quantum operations called unitaries. A unitary may have a special input state that it simply multiplies by the complex number of size 1, meaning the state does not change shape. It just picks up a phase rotation, finding the exact angle of that rotation is extremely valuable, and that is precisely what phase estimation does. QPE works by preparing two separate groups of qubits. The first group, called the ancilla or ancilla register, is put into superposition by applying Hadamard gates to each qubit. The second group holds the special input state. They Then the unitary operation is applied repeatedly in a controlled way, once, then twice, then four times, doubling each time, using each ancilla qubit as the control. Each controlled application kicks the phase back into the ancilla register, building up a binary encoded version of the unknown angle across all the ancilla qubits. Finally, we apply the inverse QFT to the ancilla register and measure it. The measured result is a binary approximation of the unknown phase angle with precision that improves as we add more ancilla qubits. Phase estimation is used in quantum chemistry to find the ground state energies of molecules, which could revolutionize drug discovery. It is also used in optimization problems and serves as a subroutine inside Shor's algorithm, which we will look at next. Shor's algorithm, published by Peter Shor in 1994, is probably the most famous quantum algorithm ever discovered. It solves the integer factoring problem. Given a large number, find its prime factors exponentially faster than any known classical method. This matters enormously because most internet security today is based on hardness of factoring large numbers. The RSA encryption system, which protects online banking, email, and web browsing, would be broken by a large enough quantum computer running Shor's algorithm. Here is how it works at a high level. Shor showed that factoring a large number or number can be reduced to finding the period of the particular mathematical sequence. That is, finding how many steps it takes before the sequence starts repeating. This period has a mathematical relationship to the prime factors that allows us to calculate them using ordinary classical arithmetic. Once we know the period, the hardest part is finding the period efficiently, and that is where QFT becomes essential. Shor's algorithm prepares a superposition of all possible values in the sequence simultaneously using quantum parallelism. The resulting quantum state contains a periodic pattern like a wave that repeats at regular intervals. Applying the QFT to this state converts the periodic patterns into sharp peaks at specific locations, a classical result from Fourier theory, now executed quantum mechanically. Measuring the output gives us the period, and from the period, classical arithmetic gives us the factors. The QFT is the quantum heart of the entire algorithm. Phase estimation and Shor's algorithm are the most famous uses of the QFT, but they are far from the only ones in quantum chemistry. Simulating how molecules behave requires finding the energy levels of the mathematical object called the Hamiltonian operator. Using phase estimation built on the QFT, quantum computers could compute these energy levels efficiently, a task that grows impossibly hard for classical computers as molecules get larger. This could transform drug discovery and material sciences by letting us simulate chemical reactions that no classical computers can handle. The QFT also plays a central role in solving a whole family of problems called hidden subgroup problems. The idea is that some mathematical structure, a repeating pattern or symmetry, is hidden inside a function and you want to find it. The The classical Fourier transform is actually the solution to a simpler version of this problem involving ordinary arithmetic, and the QFT generalizes this to the quantum world. Some problems in graph theory and cryptography belong to this family and could potentially be solved faster with quantum algorithms built on the QFT. In quantum simulation, physicists often need to switch between describing a quantum system in terms of position and describing it in terms of momentum. In classical physics, the switch is a Fourier transform. In quantum simulation, the QFT performs the equivalent operation. This is useful for simulating quantum magnets, superconductors, and another material where quantum effects are dominant. Some quantum machine learning proposals also use QFT like operations, though whether they offer genuine advantages over classical machine learning remains an active area of research. Let us trace through a concrete example to make the abstract circuit feels real. We will apply a 2 qubit QFT to the state representing the number 3 in binary. That is both qubits in state 1. We start with the first qubit in state 1 and the second qubit in the state 1. Step 1. Apply the Hadamard gate to the first qubit. The Hadamard acting on state 1 produces an equal superposition of 0 and 1, but with the minus sign on the 1 component. The minus sign is not a mistake. It is the phase flip that distinguishes 1 from 0 after the Hadamard, and it carries the frequency information we need. Step 2. Apply the controlled phase rotation with index 2 to the first qubit, with the second qubit as the control. Since the second qubit is in state 1, the rotation fires. This particular rotation corresponds to a quarter turn on the unit circle. The 1 component of the first qubit picks up this quarter turn phase rotation, shifting it by 90 degrees around the circle. The second qubit is unchanged by this operation. It stays in state 1 throughout. Step 3 applies the Hadamard to the second qubit, which puts it into the same superposition pattern but without a phase rotation, since there is no further controlled gate acting on it at this stage. Step 4. Apply a swap gate to reverse the qubit order into the standard QFT output convention. The final result is the product state where each qubit is in a specific superposition with phases that together exactly encode the frequency content of the number 3. Consistent with the QFT formula, predicts analytically 3 gates and 1 swap is all it takes. Limitations and practical realities. The QFT is theoretically extraordinary, but real quantum hardware faces serious challenges. The biggest is decoherence, the tendency of qubits to lose their quantum state by interacting with the surrounding environment. Even a tiny vibration, a stray electromagnetic field, or a single photon hitting the qubit at the wrong moment can collapse the superposition and ruin the computation. Modern quantum computers operate at temperatures just barely above absolute zero, colder than outer space, specifically to minimize these disturbances, but even so, coherence times remain very short, limiting how many gates can be applied before errors accumulate. That is also quantum error correction. That's an area of interest of mine as well. Even when qubits do not fully decohere, Every physical gate operation introduces small imperfections. A real Hadamard gate or phase rotation on actual hardware is never perfect. There are always tiny calibration errors, timing imprecisions, and crosswalk between neighboring qubits. In a deep circuit with many gates, these small errors accumulate into larger ones. Quantum error correction can in principle fix this, but it requires many extra physical qubits to encode each logical qubit reliably. Current estimates suggest that breaking standard encryption with Shor's algorithm would require millions of physical qubits, far beyond what today's hardware provides. There is also a fundamental output limitation we discussed earlier. Even if we build a perfect QFT circuit, we can only extract one classical output per run of the experiment. Extracting the right information requires careful algorithm design that amplifies the answer we want and suppresses everything else. For if you are interested in working in this field, this interplay between the theoretical power of quantum algorithms and the hard constraints of quantum measurements is one of the most fascinating design challenges in all computer science and physics at this very moment. The quantum Fourier transform is a quantum algorithm that does the same job as the classical discrete Fourier transform. It converts a representation from one domain into frequency domain, but it does so using qubits and quantum mechanics. It achieves an exponential speed up over classical methods, while classical approaches require a number of operations that grows as the square of the product of the input size. The QFT requires only a number of operations that grows as the square of the number of qubits. This is not a small improvement. It is the difference between impossible and fast. The circuit is built from just Hadamard gates and controlled phase rotation gates followed by swap gates to reorder the input and the output. Despite using only these simple ingredients, the circuit performs an extraordinarily complex transformation in far fewer steps than any classical method. The key to understanding the whole algorithm is grasping how the Hadamard creates superposition and how the phase rotation encode frequency information progressively across each qubit. The QFT is always a subroutine, never a standalone algorithm, because quantum measurement prevents us from reading all the output at once. Its most important applications are quantum phase estimation, which finds the phase angles of quantum operations, and Shor's algorithm for factoring large numbers. These have real consequences for cryptography, chemistry, and the future of computing. The main practical obstacles today are decoherence, gate errors, and a large number of physical qubits needed for fault tolerant operation. But progress in overcoming these is advancing every year. So these are your assignment questions. Conduct a research on Google Scholar or IEEE Explore and find the answers. And that's where we close this lecture.